Hey everyone, today we're going to be talking about hybridization in the context of Ochem. To review, hybridization is based on the number of regions of electron density. Any bond, a single, double, or triple bond, as well as a lone pair, each count as a single region of electron density. Let's look at the n equals 2 level for an unhybridized atom. There is one 2s orbital and three 2p orbitals. If there are 4 regions of electron density, all 4 orbitals hybridize to form 4 sp3 orbitals. If there are 3 regions of electron density, the 2s orbital and 2 2p orbitals hybridize, creating 3 sp2 orbitals and an unhybridized p orbital. If there are 2 regions of electron density, the 2s orbital and 1 2p orbital hybridize, forming 2 sp orbitals, which leaves 2 p orbitals unhybridized. Now, in Ochem, we have an added layer when talking about hybridization due to resonance. If you can draw a resonance structure in which the atom has less regions of electron density, you consider that to be its hybridization. And I'll show you what that means. Let's look at a resonance structure for this molecule. So we're going to move the lone pair on the oxygen on the right to the bond with the carbon. And now, since the carbon has exceeded its octet, we're going to move the pi bond that it forms with the oxygen on the top, pushing it onto that oxygen. So the resonance structure is going to look something like this. Now, the oxygen on the right initially looks to be sp3 because it has 4 regions of electron density: the bond with the carbon, the 2 lone pairs, and the bond with the hydrogen. However, in the second resonance structure, it looks to be sp2 because it has 3 regions of electron density: the double bond with the carbon, the lone pair, and the bond with the hydrogen. So, which one is it? Based on what we said before, it is sp2. The same principle applies to the oxygen on the top. In the first resonance structure, it has 3 regions of electron density, so it looks to be sp2. And in the second resonance structure, it has 4 regions of electron density, looking to be sp3. However, we're following the same principle, so that oxygen is sp2. Now, I wanted to look at another example and tell you guys a trick that I use to determine if this resonance will occur. So I tend to ask myself 2 questions. Does the atom have a lone pair? And is it next to an atom that is sp2 hybridized? This will indicate that it does participate in resonance. So we can check with this nitrogen. Right now, it appears to be sp3 because it has 4 regions of electron density. However, does it have a lone pair? Yes, it does. And is it next to an atom or connected to an atom that is sp2 hybridized? Yes, it does. The carbon is sp2 hybridized because it has 3 regions of electron density. So both of these conditions are checked. So I predict that in the resonance structure, we can draw one, and in that resonance structure, the nitrogen will be sp2 hybridized. So let's draw out the resonance structure and check this. So I'm going to move the lone pair to the bond between the nitrogen and the carbon, and then push out the pi bond the carbon has with the oxygen onto that oxygen. So the resonance structure is going to look something like this. Now, the nitrogen has 3 regions of electron density, so it is in fact sp2 hybridized. Now, I wanted to bring up the location of the lone pair on the nitrogen. Remember, if an atom is sp2 hybridized, it has 3 sp2 regions and 1 unhybridized p orbital. So, in which of these orbitals does that lone pair reside? Since the lone pair contained electrons that participated in a pi bond, depicted by this arrow right here, that lone pair resides in the unhybridized p orbital. Because pi bonds can only be formed from electrons in the p orbital. Now, let's look at the lone pairs on the oxygen, specifically in this resonance structure. One of the lone pairs was formed from a pi bond coming to the atom. And as I said before, electrons that participate in a pi bond have to be from a p orbital. So, one of the lone pairs on the oxygen is from a p orbital, and the other two, as normal, are from the sp2 orbital because that atom is sp2 hybridized. Thank you for watching.